I'm making this video to just kind of go over the first part of our notes on section 6.3, which is about elastic and inelastic collisions. And you should have a copy of this in front of you if you're going through this at home or outside of class. And it's worth just reading this little introduction and try to understand why we have these different types of collisions. And the first thing to notice is that when momentum is conserved, then the momentum of the entire isolated system is constant, and we don't make a distinction between the different ways that the objects in the system may interact. But if we do make this distinction in certain types of collisions, then we can do some more interesting calculations. And so this particular section or this guided notes is really just about inelastic collisions and what I'm going to call perfectly inelastic collisions. And what that means is that for us is that if two objects are come into contact with one another and then they stick together and become one object, then that is a perfectly inelastic collision. And there's some examples here, right? A meteor hits the Earth and it gets buried inside the Earth's crust. Or two cars colliding and sticking together. Those are some examples. So, and we make the note here, no collision is perfectly inelastic, but we can make the assumption in the case that the objects are stuck together after their collision. And the formula I'll get to in just a minute, the derivation is quite simple. We just begin with the idea of conservation of momentum, and that is to say the momentum of an object A and the momentum of an object B, two objects in our isolated system. When we add them together, the initial momentums that they have, then their final momentums must also add to the same number. So conservation of momentum. And this is from our section 6.2. But if we do the mass of A plus the initial speed at A plus the that's a times, plus the mass of B times the initial speed at B of B, and that's going to equal the mass of A times the final speed of A plus the mass of B times the final speed of B. And that, again, we're just conserving momentum here. But what's interesting is, of course, if the two objects stick together, then this and this are equal. So we can just go here and say MA times VAI, the momentum of the object A before, plus MB V sub BI, two objects on a collision course, and when they finally do collide, they become one. And that's our one object, and we just have a single final velocity for that one object. And really that's just the application of the distributive property right here. And so I'm just going to take that formula and put it over here in the formula section. The mass of A times the initial speed of A plus the mass of B times the initial speed of object B is equal to the mass of A plus the mass of B. Remember, they stuck together, so they're one object now. And the total mass of that object is moving at a final velocity v sub f. And this equation, this formula, just like our other momentum formulas, have the same symbols and quantities and units. And we'll just list those here. We know that P, little p that is momentum. And it has units of kilogram meters per second. And that's the SI unit. And of course, M is for mass. And that has units of kilograms. And V is velocity. And our SI unit for that is the meter per second. And just make a couple of important notes about these using this formula. Remember, velocity is a vector. Okay? It has direction. And what this really means is mind your signs. When we do these calculations, usually we're just have objects that are moving along a line or in one dimension. So in order to account for the direction, we don't have to do any complex vector mathematics with components or anything like that. We just have to maintain our signs, positive and negative, and be clear about what those mean. And also, I'm going to put another note here to use subscripts intentionally. That means, here I just use A and B to represent object A and object B. And I use I and F to represent initial and final. But, if you have a problem that involves an astronaut and a space shuttle, maybe it's M sub A and M sub S. So use those subscripts to really make it clear what object you're talking about in the context of the problem. And I'm going to just point out these three conceptual questions. And remember, when we're developing understanding about a topic like, in this case, inelastic collisions, then it's really go back to the formula and think about your answers in the context of the formula. And that will help you prepare for your formatives and summatives by just remembering that when we do a multiple choice question, usually it's in the context of one of these formulas, and if you pay attention, if you just think about the formula in the context of the question, you'll be able to answer it pretty quickly. I'll make another video that looks at one of the problems on the back for us.